Good evening. Welcome to this fourth lecture of mixed signal IC design. In today's class, we'll continue our discussion on sampling switches. In the previous class, if you remember, we were looking at sampling switches and we were looking specifically at the speed considerations. So, I defined what a speed is, what is speed with respect to a sampling circuit. Then we looked at the factors which influence the speed, and we defined to achieve high speed, we have to look at a large W bell as well as a small capacitance value. And then later we discussed about an NMOS switch, how it will conduct, a PMOS switch, how it will conduct, and a transmission gate, how it will conduct. And with that we have ended up, and we also stated that whenever you have a transmission gate switch, since it is a combination of both NMOS and a PMOS switch, the resistance is actually almost like a constant, but still we cannot say that the complete non-linearity is out here, because it is a parallel combination, and in graph it looks like almost constant, but it is not actually. And there are some other factors which also influence this, because so the moment when you say a transmission gate, even the clock and clock bar signals also should be very precise. When at the moment when the NMOS switch turns off, the same instant only the PMOS switch should turn off, right? So what I meant to say is the operation of NMOS and PMOS with respect to clock also should be precise. We'll also see those things little later. Now in today's class we'll look at the another. So yesterday I concluded the class by telling that when we look for the larger W by L and when we look for a smaller capacitance value, even though we are actually we are trying for a better speed, that will not always result in a accuracy or precision. Uh, so today what we'll see is some precision considerations of the sampling switch. So to start with, what you are seeing on the screen is a simple sample and hold circuit. So from now on, whenever I draw the clock signal, I would like to draw a realistic clock having a rise time and fall time. Right now, so depending on the switch what I use, since it's an NMOS switch, this is when the clock is high. So whenever the clock is high, we say this is sampling phase. This is sampling phase, and here the clock is low, and this phase is called as hold phase. Sometimes we call this as hold phase. This is hold phase. The other one is sampling phase. Sampling phase is otherwise called as tracking phase. Now, so if you look at the sampling phase, that is what we have seen in the previous classes. In sampling phase, we saw that if you look at the sampling phase, one is the device will be on. So depending on the switch what we use, whether it is an NMOS switch or a PMOS switch or a transmission gate switch, I would say that there will be some difficulties or some limitations. So if you look at the various limitations in sampling phase, we can say that one is from the NMOS switch, we know that it is only up to VDD minus VT. PMOS switch can conduct as low as mode VTP. So what will happen is this will definitely result in some kind of non-linearity, or that may result in some kind of distortion. So we know that non-linearity will result in some kind of distortion. In this case, it is actually harmonic distortion. We will also see that in meantime, right? So this is about sampling phase. But in the case of transmission gate switch, you have seen that there is an almost a good resistance in the case of transmission gate switch. Now today we will look at the next phase, which is actually the hold phase. So hold phase is basically when the clock is low. In the case of NMOS switch, when the clock is low, the phase is called as hold phase. And what happens is whatever a value is sampled across the capacitor. So during the sampling phase, if the capacitor has charged, the same charged value should be stored in the hold phase. That is what the hold phase meant. Right. Now, how we will start today is we will look at three mechanisms. So as I mentioned that we are looking at the precision considerations, we will look at three mechanisms which introduce error to the voltage which is already sampled in the capacitor. What I meant is I'm going to explain three different mechanisms which introduce error at the whole phase, right? So at the whole phase means when the switch turns off. So as soon as the switch turns off, there are three mechanisms, and these three mechanisms, this is actually related with the MOSFET. So three mechanisms related with the MOSFET will introduce some kind of error, and we are going to look at that one by one. Today we will see only one the mechanism, the very first mechanism. I'll just name it first, and we'll see what this mechanism is. It is called as channel charge injection. This mechanism is known as channel charge injection. Are you guys with me? Can I get a response in the chat? Yeah. So we are looking at something called as channel charge injection, right? So to explain this, just look at this same MOSFET sampling circuit. You have a whole capacitor CH, and this is the clock signal. This is clock, and this is V in and this is V out, right? Now we know that when the clock is high, what happens when the clock is high? Clock is high in the sense I'm actually giving a gate voltage which is high. So immediately what will happen? Can I get response in the chat box? When clock is high, this is sampling phase. What we are expecting is my output should be equal to V in, right? Now for output to be equal to V in, what should be present there, or how we can say that your output will be equal to V in? What is the first thing which happens as soon as the clock is high? This is what is expected. As soon as the clock is high, what will happen? Can I get some response? Yeah, capacitor is charged, right? Capacitor need to be charged, yes. Before that, or for a capacitor to charge, there should be a conducting channel, right? So what I can say is for MOSFET to be turned on, for this to be turned on, a channel should be there. Channel must exist, right? So and that will happen whenever you have a VGS voltage which is greater than or equal to threshold, right? That is the first thing happens when you when there is a clock signal high. Now if there is a channel, then we can say that in presence of channel we can confidently say that my V out will be equal to V in, because your capacitor is going to get charged. Right. Now if the capacitor is getting charged, let me just show some charges over here. Now the capacitor is getting charged through this channel, because there is a current flow mechanism happening, and as the current start flowing, the capacitor will get charged. Now can you tell me what is the total charge in the layer in the channel? The channel is otherwise called as inversion layer, because we know that this is an N MOSFET. So for an N MOSFET, the substrate is P is the substrate, and the inversion layer which is formed is of electrons, right? So on a P substrate, you have majority carriers as electrons, and we call this as inversion layer, right? Now the question here is, what is the total charge in the inversion layer? What is the total charge in the inversion layer? How can I write the total charge in the inversion layer? Yeah, it is Na, right. I'm asking about the charge Q. charge in the channel. Yeah, charge in the channel can be written as C into V. Um, it is C into V. Now, to be very precise, I can write C as the total capacitance available there, right? So we know that the capacitance of the MOSFET, the oxide capacitance, is measured in unit. It is a unit area capacitance. So this has to be multiplied by the total area of the MOSFET in order to get the total capacitance. And V is actually the effective voltage in the channel. We will write it as VGS minus VTH. This is how we generally write the total charge in the channel. Is this clear? Can I get a response in the chat? The voltage, the voltage in the channel, the effective voltage in the channel, and the total capacitance. All right. Now this can be further written as Cox into W into L into, this can be written as VDD minus, at the source node I'll write it as Vin minus VTH. Right. Now this is how I have written the total charge in the channel. Now, as I mentioned, we are not worried about, or we are not looking at what happens in the sampling phase, because sampling phase, as soon as the MOSFET turns on, there is a channel formation, and as soon as the channel is formed, a current can flow, and that will lead to the charging of the capacitor. And at this moment, say this is your clock, and at this moment when the clock transition from high to low, what happens is what immediately happens at this transition, what we are expecting is, so here the switch or the MOSFET is on, and here what I'm expecting is the switch should be off. Right. Now for the switch to turn off, what should happen? So previously, for the switch to turn on, what should happen? The channel should be created. Now for the switch to turn off, what should happen? Can I get a response in the chat? So when I writing the switch, it is actually MOSFET. For the switch to turn off, what should happen? Yeah, the channel should be depleted, or the channel should be absent, right? So that means your channel should be depleted. That means what? Now there are some charges in the channel, right? Now there are QCH is the charge in the channel. So if I write this as Q channel, this is a charge. Now what should happen? This charge should actually exit. This is a charge. Now this charge should actually exit from the, this should exit from channel. How it will exit? It can exit through two terminals. It can exit either through the source terminal or through the drain terminal. So I can say that the charge in the channel should exit from the channel through source and drain terminals. Right. So as soon as the switch turns off, all right, yes, the channel should break and the charge must be redistributed. Yes, that is very true. Or for the channel, to be precise, for the MOSFET to turn off, there should not be channel. The channel should be depleted completely. Right. So the only possibility here is that the total charge available in the channel should actually exit from the channel region, and that can happen through the source and drain terminals. And this mechanism of the charge getting removed from the channel of the MOSFET is called as channel charge injection, or the channel charge is now getting injected via the source as well as the drain terminals. Right. Now at this moment we cannot say how much is the charge which is whether the entire charge will go to source or drain. That discussion is a long discussion. We'll come to that. So let me assume that, so I'll take two cases. Case one is, I'll assume that the charge is getting injected, or the charge injection. What will happen if this charge injection happens towards the input source? Right. So if you look at the MOSFET, this is the MOSFET. Right. Now here I have a voltage source connected. So I'm just modeling it, a voltage source here. Here you have the capacitor. Now, as soon as the clock goes low at this moment, the previously charges were present in the channel. Now that charge should go to this side and this side. I'm not telling this side and this side. It can go either towards this side or towards this side, or in the other way around, source and drain. I'm not marking which is source and which is drain, but I'm considering, say for example, I am considering that the charge is getting redistributed both towards both sides, and if the charge is injecting toward the input source, what will happen? So nothing will happen this side, because what I can do is I can assume that this is a low impedance input source. If this is a low impedance, this node is again driven by this source. So I'll write this as a low impedance source driven node. If there are some injected charges, it will not affect this node. What will happen is it will be absorbed by the it will be absorbed by the source, or I can say that this charges will actually see a path, or that will not affect the input source side, because if this is a low impedance node, definitely the charges will find a path and it will get discharged over there, right? So on this side, when the charge injection is, if it is happening towards the input source side, assuming that the source is of a low impedance, I can say charges will be absorbed, or I can say there is no error is created here. If I look towards this side, I hope that is clear. Look, assuming that what I have is a low impedance source node. Now as case 2, what I will consider is I should also see the other side, right? What will happen if charge injection happens towards CH, so towards the whole capacitor. So let me just mark it as CH. This is the whole capacitor, and this is my output node Vout. Now I'm looking at the charges which are coming to this whole capacitor. So before looking at that, what we should remember is, during sampling phase, a sampled value is actually stored across this capacitor, and now that sampled value will be processed by the consecutive stages, then the very next stage of the sampling circuit. But what is happening in this, immediately when the clock turns off, as soon as the clock turns off, some more charges are getting injected into this capacitor. Now can you tell me what will happen now? Now now what will happen if some more charges are getting injected to this capacitor? What will be the effect? Charge cannot go capacitor side because it is fully charged. All right. So uh, so we know that at the moment we cannot say that the capacitor is fully charged. Now even though the capacitor is fully charged, now there are little more charges coming. There are little more charges in the channel. So definitely the capacitor should be able to hold little more charges. I don't think that will not be an issue, because when you say the capacitor is fully charged, that is with respect to the source. Now the source is not there, but you have some additional charges in the channel, right? So I hope, Tejas, it is clear. All right. Now if if I'm considering that some more charges are getting dumped or getting deposited onto this whole capacitor CH, what can happen is this can definitely change the voltage across the whole capacitor. This can change the voltage across CH. Yeah. So I can see, Pratap, you have written voltage increases. The voltage can either increase or decrease depending on the charges which is actually getting deposited, right? Right. But one thing what we can say is, definitely the value which is stored in the whole capacitor is going to get deviated. This is going to get deviated because of this additional charges. All right. Now now what we are going to do is, we are actually treating this as an error, because as the charge gets deposited on this whole capacitor CH, it introduces, or it is actually introducing an error, where it is introducing an error in the voltage which is already stored in the capacitor. Voltage stored in the capacitor. Will you agree to this? Anyway, this is an additional charge coming in. Then additional charge will definitely give you some additional voltage. That voltage can be plus or minus depending on the charge coming in, right? Are you with me? All right. So now, yeah. So we have seen now that the charges will go towards the source side as well as towards the capacitor side. And I said that if it is coming to the capacitor side, not if it is coming, it will definitely come to capacitor side, and that will actually introduce an error in the voltage which is stored in the capacitor. Now, one thing we should understand that the charge injection mechanism itself is a very complex mechanism, because finding out the number of charges moving towards the left or right is actually a complex one. There are different models actually which has come up to explain this, but none of them are that accurate. So there are many studies happen to characterize this and to minimize this effect. All those studies are there. So what we do is, for instance, what we do is, in order to study this further, what I do for now is, mm, I'll assume that the charges are actually getting distributed, or the charges are getting equally distributed at both the nodes. That is what I'm going to do now, right? That is my first study. I'll reason out why I'm doing that. So now, if the clock signal, sorry, turns off, when the clock signal turns off, the channel charge, what I'm going to do is, the channel charge is getting distributed equally between the two nodes. Each of the two nodes, the source and drain nodes. And just considering that, because I stated that it is a very complex mechanism, we cannot say that how much charge is going towards left or right. So for the time being, I am just considering that there is an equal distribution, right? That means half of the channel charge is distributed onto CH and the other half is actually distributed onto the source node, right? So this means that, this implies that half of the channel charge, Q channel, half of Q channel is distributed onto the whole capacitor CH, right? Now that will result in an error. That will result in an error. Now, how can I write that error? Now, I can say that there is a change in voltage across the whole capacitor CH, and if I write that change as delta V, and if it is equally distributed, can you tell me what is the voltage change across CH? Can one of you unmute and tell me what is the voltage coming across CH now? Because we know the channel, we know the charges, we know the capacitance value. Can you tell me what will be the voltage now across CH? We have written the Q here, Q channel. All right, yes, half of Cox WL star VDD minus, very good, yes. So what I have here is, now what I'm writing is, I'm writing the change in the voltage across CH. So it is actually WL Cox into VDD minus V in minus VT, which is the voltage, the charge divided by, I'm writing across CH. So CH I'll write here, and half of the channel, right? So half of Cox WL into VD minus V in minus VT. All right. Now, if I am looking at an NMOS based switch, can you tell me what will be the polarity of this charge? Because NMOS switch will actually give you electrons, negative charges, and the charges that is getting dumped on the capacitor will be negative. So in the case of an NMOS switch, I can actually put a negative sign over here, right? We'll also see this in simulation. Now, all right. So so if I consider that it is equally distributing, I can write the change in the voltage across CH as this. Now, actually, we cannot assume that the charge is going exactly equal, right? So why I cannot do this assumption is because I can say that in reality, um, uh, just consider about this only, because I just want to say that the charges getting distributed is not actually in a linear fashion. In reality, this fraction of charges, the fraction of charge that exits through the source and drain terminals, this is actually a complex function, is a complex function of various parameters, and to look at one, or just to look at the complexity, I can actually include the threshold voltage here. So if you look at the expression, it is minus WLCox divided by 2Ch into, if you put in the threshold voltage expression here, the actual expression, it is V in minus, you know, right? The threshold voltage expression is the native threshold plus gamma into the Fermi potential plus the VSB minus under root of 2 phi f. This is the actual expression what I can write. So one more bracket and the final bracket, right? So this itself will show that the change in voltage is actually non-linear with respect to V in. I can say that this change in voltage delta V, change in voltage delta V is actually non-linear with respect to V in. That you can see from this expression itself. Are you guys with me? Can I get some response in the chat? Right. What about others? All right. Now, what you can conclude here is now look at the charge here. So now you will be wondering why we are actually considering the small charge which is dumped onto this capacitor. See, you can see that the additional charge is actually dependent on this input voltage V in, right? So that means at every instant, whenever the clock turns off, the amount of charge which is getting dumped onto the capacitor is actually different. It is not a constant voltage which is getting changed, or this delta V is not at all constant, because it is actually depending on the input voltage, right? So now what we can say is, if the channel charge now, so this, since this charge injection is signal this charge injection is actually signal dependent. This is signal dependent, and if it is signal dependent, it is actually giving some non-linearity. At least from the expression you can say that there is a non-linear expression. If there is a non-linearity, that can actually result in some kind of distortion, and as we have seen in our previous course, maybe not everyone, we have seen that non-linearity will always result in some kind of distortion, and one such distortion is harmonic distortion. We'll come back to this later, right? This is just for understanding, I'm just telling here. All right. Now, so what we did is, what we understood is, as soon as the clock turns off, some of the charges will come and sit on the capacitor. That is going to alter the voltage which is already sampled in the capacitor. Initially, we assumed that the charge is getting distributed equally, and but that also can result in some error. That we have written the error in this form. Later, we saw that this change in voltage is actually a nonlinear function of V in. In that way, I can say that this nonlinearity can even result in harmonic distortion, right? Now, we'll get a clarity if you look at the spectrum at the output. Now, worst case, what can happen? So, if I want to look at the worst case scenario, worst case, what can happen is, the entire charge will get dumped onto this capacitor. That the worst case scenario is only that, right? The entire channel charge, that also we'll consider. The entire channel charge is injected onto CH. That is only the worst case which can happen. Now, what will happen if this entire channel charge is going to get dumped onto this capacitor, right? So, for the time being, I'm just neglecting the non-linearity through threshold voltage. So, in that case, I can write my V out is equal to V in. This is what actually happening. V out will be equal to V in. But now, what will happen? I have an additional voltage here, which is V in minus delta V. Are you guys with me? Can I get some response? Now I'm looking at the worst case scenario of the entire channel charge is getting injected onto the capacitor. So initially I assumed that initially what I'm thinking is V out is equal to V in, right? But now as soon as the charge get, as soon as the clock turns off, some of the charges is getting dumped onto the capacitor, and if I'm considering as an NMOS switch, that is actually a negative voltage, so I can write this as V in minus delta V. Now what is this? You can further write this as V in minus delta V is, as we have written before, WL Cox into VDD minus V in minus VT. Previously I have written half 50. I assume that there are yeah, Naveshir, your question is V out should increase. Yeah. So what I was telling is, if the switch what I'm considering is an NMOS switch, the charges coming over will definitely, I can the charges coming over are electrons, the negative charges. That is why I have just put a negative charge over here, negative sign over here. Are you getting that? All right. Yeah. So in the case if you have a PMOS switch, it is actually ulta, right? It is other way around. Now, WL Cox in VD minus V in minus VT divided by CH. Previously, I have written 2, assuming that it is 50%. Now, I have taken the worst case scenario that the complete charge is getting dumped onto this capacitor. Now, I'm just rearranging this equation in this form. V out is equal to, there are V in terms together. I'm just taking V in terms together. So, V in into 1 plus WL Cox by CH is there. That is a first term, and then minus I'm taking then WL Cox by CH into what I have is VDD minus VT. VT is a threshold, right? Now so if you look at this expression, what I'm expecting is V out should be actually equal to V in. Actually this is a term, V out should be equal to this is an additional term over here, and this is also an additional term, right? But these two are not expected, but this has come because of this charge injection, right? So this expression suggests that this output, this V out suggests that the output deviates. So V out is should be equal to V in, but now that output is deviating from ideal value. And how it is deviating, there are two terms coming up, right? So I can understand that as two fx, through two fx. One is, you can see that what I need is a unity gain, right? V out should be equal to V in. What I need is a unity gain, but now I have a non-unity gain. What is a non-unity gain here? The non-unity gain here is 1 plus WL Cox by CH. That is one thing which is actually deviating the output from the ideal value. And one more is, the second thing is the second term, which is actually, if you look at the second term, WL Cox by CH is constant, VDD minus VT is also constant. So I can consider that this is actually a constant offset, right? So what is a constant offset voltage? This is a constant offset voltage is a second effect. So that is minus WL Cox by CH into VDD minus VT, right? So the first one is actually causing an error in gain. Therefore, we can say that this term is actually this is actually a gain error term, and the second term is actually introducing a constant offset voltage, right? Now if you look at the cara if you look at the input output cara of a sample and hold circuit, so this is V in and this is V out. So ideally how it should be, your output should be equal to V in. So the ideal response, what we are expecting is something like this. This is your ideal graph. But now how the graph has modified, in a slightly different way, because if you look at the expression, there is a there is an offset which is a negative value, and the charge is actually, there is a non-unity gain. The gain is not unity, it is more than 1. So I can redraw the graph something like this, in this form, right? This is the offset, and This is the actually the graph with charge injection with offset as well as the gain error. Right. So what this graph is actually the input output carrier of sampling circuit with charge injection. All right. So what we understood is, if the charge is getting dumped on the capacitor, it is going to introduce an error, and that error, we have looked at that error, and the worst case scenario we have taken, and we have seen that it is basically the output is deviating because of two things. One is gain error, and another is a constant offset voltage. Right. Now maybe I'll wind up here. We'll continue from here in the next class. Uh, all right, I may stop recording and I have a few more announcements. Yeah, so what we saw today is, I'll just quickly, we have looked at we have not come to the precision considerations yet. We have looked at I stated that there are three mechanisms which is going to introduce some error in the whole phase, and the very first thing is charge injection. As soon as the clock turns off, the channel charge has to go somewhere. It can go either to the left or to the right. We have looked at both the cases, and we have also taken the worst case scenario, and from that we understood that there is a deviation in the input output carrier of a sampling circuit. So we'll see from here in the next class.